this is my lab report on charged tapes. So first of all, the purpose of the lab is to determine the amount of excess charge present on an electrically charged piece of tape using our knowledge of gravitational force, electrical fields, and electric force, as well as to estimate the amount of charge present on each tape that is needed to have one float above the other using a computational model. So the main results were that one piece of tape had a positive 1.8 times 10 to the negative 8 coulomb charge from part 1 of the lab, and then it was deficient in 1.125 times 10 to the 11 electrons with 2.98 times 10 to the negative 7 electrons per atom. And for the estimation of charges when they act as a line of charges on the tape, it was Q is equal to positive 3.2 times 10 to the negative 8 coulombs. So some key principles that we want to know before we go into this lab is Coulomb's law, first of all, that the magnitude of the electrical force is equal to 1 over 4 pi epsilon 0 times Q1 times Q2 over R squared. In this case, we assumed that Q1 is equal to Q2, so we can simplify the numerator to be Q squared over R squared. And then the force due to gravity is calculated multiplying mass times g, where g is 9.81 meters per second squared. And then we need to also understand Newton's second law, where the sum of all forces acting on the system is equal to mass times acceleration. And in a static, when a system is in static equilibrium, like the tapes in this case, the net force is equal to 0. And then we also need to understand charge interactions. So like charges will repel and opposite charges will attract. So some brief background in experimental design. Here you can look at the procedure here with what the actual experiment looks like. And so for the initial conditions, the system is tape B with the surroundings being tape A, earth, and basically everything else. The length of the tape is 0.199 meters, the width of the tape is 0.019 meters, and then the mass of the tape was 1.99 times 10 to the negative 4 kilograms. So we acted under the assumption that the U-tapes are equal in charge and the charge is equally distributed along the pieces of tape, as well as air resistance being negligible. And for part 1, we assumed that the tape pieces acted as a point charge each in the center of the tape, and then as a line of charges for part 2. So the calculations for part 1, first I started with, I measured the distance between tape A and tape B when tape B was floating above tape A. I got that to be 0.0381 meters. And then I set the magnitude of the gravitational force equal to the magnitude of the electrical force and solved for Q, where I got 1.8 times 10 to the negative 8 coulombs. I divided that by the charge of 1 electron to get 1.125 times 10 to the 11 electrons deficient. It's deficient because it's a positive charge, as found by the fact that it was attracted to the negatively charged pen. For the fraction of atoms, I found the area of one atom, and then I did the surface area of the tape divided by the area of the atom to find the atoms per tape, and then I used that number to get the number of electrons per atom, which was 2.98 times 10 to the negative 7. So the computational model, my number for the charge of the tape was 1.7745 times 10 to the negative 8 coulombs, which is pretty similar to what I got for my calculated thing. It's a little bit less than what I got, but I'm just going to assume that's from rounding errors due to the calculator. But here you can see that the electrical force, which is this one, and the gravitational force are equal in magnitude in opposite direction. This orange dot here is tape B, and this cyan dot is tape A. So for part 2, it's a little more complicated code. So first, when I ran this code, I got a significantly smaller arrow for the electrical force than the gravitational force. And so what I did was I found the ratio between the magnitude of the gravitational force and the magnitude of the electrical force, and then I took the square root of that number and multiplied it by the charge that I got from part 1, and that gave me a new charge of 3.2 times 10 to the negative 8 coulombs, and then when I plugged that in as the new Q value, I got equal vectors, but opposite in direction, or, well, they're approximately equal. They're a little bit off, but I do think it's partially due to rounding error, like I said before. So sources of error, the tapes may actually have differing charges, meaning that Q cannot be as easily like Q1 times Q2 cannot easily be simplified to Q squared, which would make our estimation inaccurate. Additionally, like the mishandling of tape could have redistributed charges, air resistance and humidity could have affected results, and then measuring errors or rounding errors due to calculator precision. So for the what if we reverse the signs of protons and electrons, ultimately our observations would be the same, as the interactions would not actually change. Negatively charged objects will still be attracted to positively charged objects, and like charges will continue to repel. Now, the charge calculated from the computational model for part 2 was significantly larger in magnitude than the one from part 1, because the line charge model is a lot more precise and a lot more accurate, because in real life, when we're looking at a piece of tape and there's a bunch of charges on it, it's more accurate to say that it's distributed in a line of charges across the surface rather than a singular point charge in the center.